At exactly 2 times the gravitational constant times mass divided by the speed of light squared, the very geometry of space becomes a one-way street. This specific distance, known as the Schwarzschild radius, represents a mathematical threshold where the escape velocity exactly equals the speed of light. Consider the escape velocity formula as a function of radius. As the radial distance decreases toward the Schwarzschild radius, the required velocity for escape increases toward a vertical asymptote at the speed of light. Mathematically, no real number solution exists for escape beyond this critical limit. The ratio of observed frequency to emitted frequency is governed by the square root of 1 minus the Schwarzschild radius over the current radius. As the object approaches the horizon, the denominator of the interior fraction nears 1, causing the frequency ratio to approach 0, resulting in infinite redshift. Time dilation is the reciprocal of the redshift function. For a distant observer, the time interval on a falling clock appears to stretch toward infinity. We express this as the limit of delta t prime as r approaches the Schwarzschild radius, showing that time effectively stops from an outside perspective. In a space-time diagram, light cones represent all possible future paths. Near a black hole, these cones tilt inward. At the event horizon, the entire future light cone is rotated 45 degrees, such that all future paths point directly toward the singularity, making outward movement mathematically impossible. At 1.5 times the Schwarzschild radius, gravity is strong enough to force photons into a circular orbit. This is the photon sphere. Unlike stable planetary orbits, this equilibrium is unstable. A fractional deviation in a photon's path sends it either spiraling into the abyss or escaping into space. A crucial distinction exists between coordinate time and proper time. While coordinate time diverges to infinity at the horizon, the integral for proper time remains finite. The falling observer crosses the horizon in a measurable, limited amount of time, despite what the rest of the universe perceives. Inside the horizon, the radial coordinate and the time coordinate effectively swap roles. The march toward the center becomes as inevitable as the passage of time. The curvature of spacetime, calculated by the Riemann tensor, increases as a function of 1 over r cubed, peaking at the central singularity. The surface gravity at the horizon is inversely proportional to the mass. For smaller black holes, the gradient is steeper, leading to higher Hawking temperatures. This relationship links thermodynamics to geometry, where the area of the horizon directly represents the entropy of the system. Modern physics suggests that all information about an object falling into a black hole is encoded on the two-dimensional surface area of the horizon. This holographic principle implies that the volume of the interior can be described by the functional properties of the surface boundary alone.